Hello everyone. In the previous video we have seen how to train or fit a regression model using the Scikit-learn library of Python, and in that demonstration we have used the Boston housing dataset. In today's video we are going to use the same dataset for illustrating the other two regularized or penalized regression methods, which are called Lasso Regression and ElasticNet Regression. In the regression model, it is a biased model because it adds a penalty term to that of the sum square of error, and the penalty added in regression is an L2 norm of the weight parameters, which is the sum of the square of the parameter estimates. So here alpha times the sum square of the weights is the penalty term, and here due to the squaring process large weights will be penalized more than that of the smaller weight parameter estimates. And the introduction of the bias in the regression actually decreases the training performance, but this decrement in the training performance could result in a higher generalization ability or a higher testing performance. And the other here, the penalty will make the weight parameter estimates to approach to 0 as the penalty is larger, specifically when the penalty parameter or the ridge parameter alpha is larger. And this ridge regression, lasso regression, and ElasticNet regression are also called shrinkage methods because they force the weight parameter estimates to shrink to that of the value of 0. And specifically regression is mostly applicable if we have covariates or input features which are multi-collinear. So the procedure for training using the Scikit-learn library is from a sklearn linear model we need to import the ridge class, and after importing this ridge class we have to instantiate our model of interest, and this is just an instantiation or creation of a certain container for storing the model that's going to be trained. Then once we instantiate the model of interest, next we need to call the method fit over this instantiated model and pass that of the training input features data and the training output data, and after that the model will be trained. And after that we can extract the intercept or bias and the weights or the coefficients of the regression model using the attributes intercept underscore and cof underscore. And for the model performance we can also call the method score, and we have to pass either the training data to obtain the training score or training R square, or we can pass the testing data to obtain that of the testing R square. And we have to keep in mind that since we have here a penalty term, the penalty may not have a consistent impact if the covariates have different scales. So it is essential to either standardize or normalize each of the covariates that are included in the dataset being used for training. So today we are going to consider that of the Lasso regression and ElasticNet regression models. So in the Lasso regression, actually here Lasso means is just an abbreviation, least absolute shrinkage and selection operator. Shrinkage, it is like that of the ridge regression model. It shrinks the weight parameter estimates toward 0, and here specifically for Lasso regression we have the term, let's say, selection. This is to refer to that this lasso regression can be used like a method of variable selection. So this lasso is nothing but just this abbreviation, least absolute shrinkage and selection operator. So like that of the ridge regression model, lasso regression model is also a biased regression model, but here the penalty is going to be an L1 norm, or is going to consider that of the sum square of the absolute values of the weight parameter estimates. So unlike that of the ridge regression penalty term, which contains the sum of the square of the weight parameter estimates, in the lasso regression we are going to use that of the sum of the absolute value of the weight parameters. So this is called L1 norm, or in matrix notation we can utilize this one. And the other, unlike that of the ridge regression, here since the penalty is a function of the sum of the absolute values of the weight parameter estimates, so the penalty gives equal weights for each weight parameter estimates, or the penalty is the same for each weight parameter. Therefore the penalty is equal or the same for each weight parameter. But for that of a ridge regression model, since the penalty is a function of the sum of the square of the weight parameters, so the impact of the sum of the square of the weight parameters is different for different weights parameter values, or specifically due to the squaring process, large weight parameter estimates will have larger impact due to the penalty or due to the squaring process. And the other, in the ridge regression, the parameters are forced towards too close to zero. So ridge regression shrinks those weight parameters to zero, but lasso regression, in addition to shrinking the parameter estimates towards zero, it sets some of the weight parameters exactly equals to zero. Therefore, lasso regression not only performs regularization like that of the ridge regression, but it also conducts a sort of what you call feature selection. Therefore, those features whose weight estimates are zero can be considered as unimportant variables, but those covariates with weight estimates different from zero can be considered as important covariates. So now let's see how to train this lasso regression model. We have to import this lasso class from a scikit linear model like that of coding linear regression for OLS regression model, and that's of ridge regression method of polling. We just use from a scikit linear model import lasso. Now this will be imported, then we can run this cell. Now the class lasso is imported. Then before fitting or before trying to fit this lasso regression model, first we need to create a container where the model to be trained is going to be stored, or we have to instantiate our model of interest. So here our model of interest is lasso, so let's say lasso, and let's assign the object name lasso reg, and let's call this object lasso reg. So if I run this, it displays this orange colored results. So here we can click on the parameters. Here we have alpha 1.0. This is just the usual shrinkage parameter like that of the ridge regression, or this alpha is nothing but this value. Therefore by default alpha is 1.0, or it is just 1. Now the model is instantiated, or a lasso regression model is instantiated with a default shrinkage effect of 1. Now this model is not fitted yet, and if you are interested, you can look at the documentation for Lasso by clicking on this object having a question mark symbol. So by default the value of alpha is 1, and there are also additional parameters. You can just look at them. Then once we instantiated our model of interest, next we need to train our model. To train our model, we need to call the method .fits on our instantiated model. This one, .fits, and we have to pass our training datasets. The input features training dataset and the output feature training dataset. Then we can simply run this cell. Now the color changes from something like an orange to that of something like a light blue. Therefore the model is trained, or if we point to the symbol having like an eye, it says fitted. Now the model is fitted and the parameters are the same, the ones that we have already instantiated here. Then now the model is trained, or the model is already fitted. We can extract the parameter estimates if we are interested, using that of the intercept underscore and cof underscore attributes of this trained model. But now before that, let's generally see how the Lasso coefficients are, because unlike that of the ridge regression, we say that this Lasso regression model sets some of the coefficients actually to be 0, in addition to that of shrinking the values towards 0. So here, for example, we instantiate a model with alpha, let's say 0.1. In the previous case we used just the default shrinkage effect, but now let's change this alpha value to 0.1. This is the instantiation of the model, and this is the fitting. And after that, once we fit the model, we can extract the weight coefficients using cof underscore. So let's plot and see how the coefficients, how the coefficient values are. So here we have the covariates marked along the x-axis, and here we have the coefficients. So for example, the weight coefficient for crime becomes 0, for Zn 0, for this variable index again 0, and for NOx again 0, and for age the same, and for rad 0, and for tax 0. Therefore, like that of the ridge regression model, this Lasso regression model in general shrinks the parameter estimates towards 0, but besides to shrinking the weight parameter estimates towards 0, it also sets some of the weights coefficients exactly equals to 0. Therefore, it plays something like a method of feature selection or covariate selection. Specifically, if we are interested, we can look at these weights coefficients by extracting from the trained model. So let's say Lasso coef. So here exactly just the first 3 variables are set to 0, and here another variable is also set to 0, here another variable, and so on. Therefore, of this totally I think 13 covariates included in the model. Based on this specification of penalty of 0.1, there are only 1, 2, 3, 4, 5, 6 important variables, but the others are assumed to be unimportant because it sets their corresponding weight coefficients to be 0. So here, by the definition of this Lasso regression, if alpha is 0, that means we are minimizing the sum square of the error. Therefore, in that case, the lasso regression will be equivalent with that of the usual OLS regression model. So here let's evaluate the model performance using that of the default value of alpha and that of, let's say, setting the value of alpha to 0.1. Using the default, we can instantiate the model as lasso, and then we have to train the model. And after that, once we train the model, we can call the method score and pass the training set to obtain the train score or train R square. And we have to again call the score, and we have to pass the test data in order to obtain that of the test R square. So if I simply run this cell, now this is the training R square, which is about, let's say, 26.34%, and this is that of the test score, which is 24. Let's say 5.6. So when you use the default shrinkage effect, that is 1, the performance of the model in both the training and testing set is poor. Even a random model is expected to produce a 50% R square, but it is below 50%. So the default level of alpha is not good. Rather, we have to tune this shrinkage effect using that of the grid search parameters. On the other hand, for example, if we set alpha as 0.1, here we have to say alpha equals 0.1, and after instantiating this model with alpha is equals 0.1, we have to fit the model on the training sets, and after that we can extract the score of the training sets and the score of the testing sets. Let's run this and see the difference. Now, when the shrinkage effect for the lasso regression goes from 1 to 0.1, now the performance of the lasso regression in both the training and testing sets is improved. So in the training set it is around 70.4%, in the test set it is around 65.9%. Therefore, in general, just we cannot simply specify any value of the shrinkage effect. Rather, we have to tune, or we have to search for the value that optimizes the performance of the model in both the training and testing datasets. So now let's see how to tune this alpha hyperparameter or the shrinkage effect using that of grid search. A grid search is nothing but it is a way of just fitting a model for each hyperparameter value. Then after fitting the model for each hyperparameter value, we are going to select the hyperparameter value that produces the better performance or the better, let's say, generalization in that of approximation ability. So this grid search CV is nothing but here just we need to import from a scalar model selection, and then it should have an estimator. The estimator is nothing but the regression model. For example, for our case, it could be that of the lasso regression. And the parameter grid is nothing but it is a dictionary consisting of all those possible values of the hyperparameters. And there are also other parameters that can be specified here. So the way that we are going to use this grid search CV is the same with that of the one that we have used in the ridge regression. So first we have to instantiate this grid search CV or grid search cross validation, and after that we need to call the method fit, and we need to supply the training data. Then that fits the model for each hyperparameter value that are specified. And if we are interested, we can obtain also the R square value of the model utilizing that of the optimal hyperparameter values. And then once we fit on this grid search cross validation, once we fit the model by supplying the training data, we can get the best hyperparameter values and their corresponding best R square scores. So let's see it. Just first we have to instantiate the estimator, that's model of our interest. Now our model of interest is Lasso Regression, so let's instantiate as Lasso and let's assign this name Lasso Reg. Now we have instantiated our model of interest. Next, here in the parameters we have alpha, by default is 1.0, but now we are going to consider a set of values. Instead of just this specific value, we are going to consider a set of values. So let's define these hyperparameter values of the shrinkage effect. So for this shrinkage parameter alpha, we are going to consider NP linear space 10, let's say NP linear space 10. This is just selecting 10 values from 0.1 to 2, which are evenly distributed. Let me run it. Therefore here we have the first value 0.1, second around 0.31, 0.5, and so on, finally 2. Selecting just 10 possible values for the shrinkage effect or alpha. So here let's define just param values as name of the hyperparameter alpha and the values, this one. This definition is nothing but these values. It's advantageous to increase the number of values, but it will be computationally expensive. Otherwise you can make this 100 or even 1000, but since it is going to fit a single model for each hyperparameter value, computationally it will be expensive when we have a large number of hyperparameter values. So let's run this. This one, what is it? 1000 param values alpha and linear space 10. This is, there should be only 10 values. Okay, oh sorry, so here just this should be, here I am calling another variable, so no, here param values I need to call here, therefore it should be 10. Yeah, here the name of the hyperparameter is alpha, the values are this one, therefore there is just a dictionary with the name of the hyperparameter and their corresponding values. Now we instantiate our model of interest here, and we defined the values of the hyperparameter alpha here, and then now we are going to use that of grid search CV or grid search cross validation. Therefore when it says grid search, it is nothing but just training a single model for each hyperparameter value. In the case of having 2 or more hyperparameters, it is going to consider every possible combination, but for now we have only a single hyperparameter. Therefore this grid search CV is going to fit a single Lasso regression model for each alpha. That means particularly for this case the grid search CV is going to fit 10 different models, and of those 10 different models it will select the one having a larger or better performance. So this grid search CV has an estimator, which is our model of interest, and here we have the parameter grid, that's the list of the possible values of the hyperparameter, and we need to also define here the number of cross validations. By default is none, but we have to define something like 5 or 10. Again, increasing the number of cross validation will not hurt, but it will be computationally expensive. So estimator, we say lasso reg. This is nothing but the one that we have instantiated here. And for the param grid, we have defined here param values. So param grid equals param values. And number of cross validations, 10. Therefore, the training data is going to split into 10 different folds. And under each fold, each of the split will be considered as a testing or validation set, and the remaining 9 splits will be considered as training sets. And this is just to return. By default, it returns that of the test score, but to return that of the training score information again, we can set this as true. Now this is not fitting, but this is instantiation of again the grid search CV. Let me run it. Now it says grid search CV. If I point to here, it says not fitted. So this grid search CV is instantiated, but not fitted or not trained yet. So here we have parameters. The parameters, the estimator is lasso, the one that we have defined here, lasso regression, or specifically this one. And param grid, here we have alpha. This is the hyperparameter value. Array says 0.1 up to it says 2. So this is again the one that we have defined here, or these values. And the others are just that are not that much required parameters. And on the estimator, if we click on lasso, this shows the parameters. Now by default it is 1, but now this grid search CV will change these values to 0.1 and get the score, and again 0.3 and so on up to lots of 2. So let's minimize this. Then here we have instantiated the model, and the color here for this output is like something blue. Now on this instantiated grid search CV model, we can call the method fits, and we have to supply the training data, training input features data, and the training outputs data. Then let me run this. Yeah, now the fitting or the training is completed. If I point to here, it says fitted. Let me click on here and let's see the parameter. This is the one that are already defined in the grid search CV. Let's consider that of the best estimator. So here the best alpha is 0.1. Now for example here, the smallest value that we have is 0.1, right? So this is smallest value of these 10 different values. This smallest value is the best optimal shrinkage effect. So 0.1, yeah, this is the best hyperparameter value. So here we have already fitted this grid search CV model, so we can extract this the optimal hyperparameter value, and also we can extract the optimal R square value. And for that, over that of this lasso grid, the one that we have trained here, or this one, we can call best params. Then this will display the optimal hyperparameter value, that is 0.1. and we can also obtain its corresponding R square value. So here the best R square value is obtained through using the attributes best score underscore. Let me run it. Now the number of cross validations are 10 here. Therefore, when we use this hyperparameter value, that is 0.1, the average performance on the 10 folds becomes 66.1%. This is the average performance of the lasso regression with the hyperparameter 0.1. But here, as I said before, on the number of values assumed to the hyperparameter, we can increase this. Increasing this will never hurt, but it will be computationally intensive. So here, for example, it selects 0.1, which is the smallest value in our hyperparameter values grid. Therefore, for example, instead of starting from 0.1, let's start from 0.01 up to 2. Now the smallest value here is going to be 0.1. So let me again instantiate this model, and let's define the hyperparameters here starting from 0.01. Previously it was 0.1, but now we changed it to 0.01. Let's train the grid search, or let's run this grid search CV using these hyperparameter values. Let me run it. Now it's done. Let's fit. Now the cross validation CV is fitted, and let's get the optimal value 0.01. Now 0.01 is actually this, the smallest value, right? Let's change it further, and let me run again starting from the instantiation, and again this one. Now the smallest hyperparameter value 0.001. Let's instantiate the grid search, and let's fit the grid search model. Done, and let's get the optimal value of the shrinkage effect 0.001. Therefore, every time when you change the values smaller, therefore this grid search CV is selecting the one which is the smallest one. Therefore, overall, that means this indicates that setting this alpha parameter value to 0 may be better, or using the usual OLS regression would be better. But it is just the way how to search the optimal values. I'm just showing you here, defining the value, the optimal values, the lasso grid search, and fitting the model, and the optimal value. So every time just the smallest value of the hyperparameter is being selected. That means every time, as long as we go close to 0, just this hyperparameter value is being selected. Then that means this lasso regression is equivalent with that of the usual OLS regression model. But the way that we are going to optimize, or what you call tune the hyperparameters in this form, we have to instantiate our model of interest, and we have to define the grid values of that of the hyperparameter, and then we have to instantiate the grid search CV, and we have to train the grid search CV model, and then we can extract the best optimal hyperparameter values and also the best R square values. Now, instead of focusing on a single particular value of these shrinkage effects, let's see how the different values of this shrinkage effect affects the weight parameter estimates. So for that, for example, here I instantiated a lasso regression model with the default shrinkage effect, but now we are going to consider a set of values, let's say from this is a log space, so values from 10 to the power of minus 3 to 10 to the power of 1, and let's select 50 evenly distributed values. Then these alphas are going to replace the default values inside here, which is 1. Then we collect here the weight coefficients, and we set the parameters based on this specification and train the model, and then append the coefficients here in this empty list. And this is just the code for plotting the weight coefficients or the weight parameters of the lasso regression. Now this is the plots for different values of shrinkage effect or alpha, the regression coefficients, specifically the weight coefficients. Now let me go back first to that of the ridge regression. So previously we have seen that in the ridge regression, when the ridge coefficient as the ridge coefficient or the shrinkage effect increases, all the parameters will go to 0 at the same time. Right? Initially they were different, but at a certain time, let's say starting from even, let's say 10 to the power of 2, they all the parameter coefficients of the coverage close to 0. But when we come to that of the lasso regression, here initially they are different. For example, some are when the alpha value or shrinkage effect is 0.001, some are around, one is around minus 20 and the other minus 15, and some are around 10, and so on. But when we increase this shrinkage effect, some of them immediately went to 0 or goes to 0, and the remaining goes to 0 later. But in the case of ridge regression, all the parameter estimates or all the weights coefficients of the coverage goes to 0 at the same time. But here some of them may die early and some of them may die late. So this is just how this shrinkage effect affects the weights coefficients of the coverage in lasso regression. So lasso regression shrinks some of the coefficients, and this literally translates into that of what we call feature selection. So, and the other here, when alpha is 0, actually based on this specification of that of the objective function of the algorithm here, when alpha is 0, the one that's going to be minimized is this sum square of error. That means it is going to seem that this lasso regression is equivalent with that of the OLS regression when this alpha is 0. Now let's set this value to 0 and let's see the outcome. So here I instantiate, let's say, lasso with alpha equals 0. Let me break into two lines for ease of just clarity. Now this is instantiation, so let me run it. Now the model is successfully instantiated, or the container is created. Now let's fit the model. Lasso reg, we have to call this method dot fit the training data. Let me run. Therefore here, even if by definition when the lasso shrinkage effect is 0, even if it seems to obtain that of the usual OLS regression model in scikit-learn, setting alpha is equals to 0 will not fit the model or will not train the model of interest. Therefore, in that case, if alpha is to be 0, instead of setting alpha here 0 in the lasso regression model, it is better just to directly fit that of the OLS regression model from scikit-learn dot linear model, import linear regression. Then we have to, as usual, we have to instantiate our linear regression model. Let's say here linear regression, and we do not have alpha here, and let me say just this lin reg, and this one again lin reg. I have to run this, and now the linear regression model is instantiated. Then I have to use or call the method fits, and then xtrain ytrain. Now the model is trained. Therefore, in case if alpha has to be set in the lasso regression, this will not work, or this will not train the model with alpha is equals to 0. Therefore, in that case, we have to directly fit the OLS regression model. But by definition, when alpha is 0, just lasso regression should be equivalent with that of the OLS regression model. And the third type of penalized or regularized regression model is called ElasticNet regression. Now this ElasticNet regression model combines both the L1 norm and L2 norm penalties of that of the ridge regression and lasso regression. So it combines the effect of both ridge and lasso regressions. Therefore, here we have the sum square of error as usual plus penalty. But now the penalty combines both of these two penalties, L1 norm and L2 norm. The L1 norm is nothing but as usual just defined. Let's say alpha 1, and this the sum of the absolute value of the weights parameter estimates, and plus alpha 2 times the sum square of the weights parameter estimates. In matrix notation, it can be written in this form: just alpha 1 L1 norm of W plus alpha 2 L2 norm of W. This is the definition of ElasticNet regression, but the way that ElasticNet regression is parameterized in scikit-learn is a little bit different. Therefore, instead of this functional form, the parameterization in scikit-learn is in this form: alpha times L1 times the L1 norm of the weights plus alpha times 1 minus L1 times L2 norm. Therefore, the actual parameterization in scikit-learn is this one. Therefore, with this parameterization, for example, if L1 is 0, if it is 0, this will be removed. Then that means the model will be similar with that of the ridge regression model. But if L1 is 1, in that case, this component will be 0. L1 is 1. Then in that case, the model will be similar with that of the lasso regression. And the other, if alpha is 0, both of these penalty terms will be 0. Then in that case, this will be similar to that of the OLS regression. So now let's see how to train an ElasticNet model. So with the same way that of calling linear regression, ridge regression, and lasso regression, from a scalar linear model, we need to import the ElasticNet class. Then let's start from just setting this. Here we have L1. And the other here, L1 is actually it measures the relative amount of the two penalties. Then, for example, if L1 is 0.1, then the weights of the penalties in this objective function are equal. Therefore, this L1 captures the relative amount of the L1 penalty, or let's say that's of the L2 penalty. So L1 should be somewhere a value between 0 and 1, because just the relative amount of, let's say, this penalty. So where L1 is 0.1, both the L1 and L2 penalties, or both the effect of both ridge and lasso regressions, are equal. Otherwise, the impact will be different. So we need to import ElasticNet class from a scalar linear model. So we have to run this cell, and let's set L1 to 1. Then we have to instantiate using ElasticNet. Now here we have two hyperparameters. In the ridge regression, we have only a single hyperparameter, that is alpha. In the lasso regression, the same, we have a single hyperparameter alpha, but in ElasticNet regression, we have two hyperparameters, alpha and that's of this L1. So now let's fit an ElasticNet model by setting L1 equals 1. This L1 is actually ElasticNet reg. Let's instantiate. This is an instantiation. Just run. Now it is not fitted yet. We can look at the documentation. Now L1 ratio is by default 0.5. That means the impact of both the L1 and L2 penalties are equal, or the impact of both, let's say, the ridge effect and that of lasso effect are the same in the ElasticNet model. But now we set it to 1. Here we set it to 1, L1 ratio. Then we can fit the model by calling this fit method. So we have instantiated, then we have to fit by supplying the training data. If I run this, now the model is fitted or trained. We can examine the parameters here. Alpha is 0.1, the one that we have specified here. L1 ratio, it is just 1. We can also get that of the weight coefficients. We can run this. Then it sets some of the coefficients to 0, because ElasticNet combines the effect of both the ridge regression and lasso regression. Due to the lasso regression, that's of the weight parameters will be forced towards 0, and no, for that of the, because of the ridge regression or the ridge effect, the weight parameters will be forced towards 0, and because of the lasso, some of the weight parameters will be forced to be exactly 0. So that's why here some of the parameters are exactly 0. Therefore, setting L1 equals 1 in the ElasticNet is the same as lasso regression. Setting here L1 equals 1, it is the same as that of lasso regression. So these are the parameter estimates. Let's call, or let's fit that of a lasso regression model. ElasticNet. Now let me fit that of Lasso Reg. Let me say this to Lasso, and here I do not have L1 ratio in Lasso Regression, and then I can instantiate the model. Now it's just the instantiation. We can fit the model by calling the method fit xtrain ytrain. Now the model is fitted. I can just directly extract here the coefficients, the weights, parameter estimates associated with that of the covariates. I have to use the attributes of. So when you set L1 ratio 1 in the ElasticNet regression, it is exactly the same with that of Lasso regression. So these are 0. The same. So these parameters must are exactly the same. So by setting L1 ratio to 1 in the ElasticNet regression, we can obtain exactly the same parameter estimates of that of the Lasso regression model. Now let's set the L1 ratio to 0. Let's set this L1 to 0. And in that case, if we set this L1 to 0, this component or the L1 norm will be removed. What we will have is something like a ridge regression. That is what we would expect. So here let me say alpha 0, L1, I can use any value. Then if I try to run, no, it results an error. Right? Therefore, in the case where alpha is 0 here, instead of fitting the model through that of ElasticNet, it is better to directly fit that of a ridge regression. That is just ridge. Ridge reg, we have to call instantiate the model, and then we have to ridge reg dot fit. We have to supply the x train and y train, and after that we can obtain the coefficient estimates reg dot coef underscore. Therefore, if alpha is 0, when alpha is 0, what I missed here. Okay, yeah, sorry. Here, when alpha is 0, both of these components will be cancelled out. So what we would expect is an OLS regression, not that of a ridge regression. So we expect that of a linear regression or OLS regression model. We have to fit this model. Therefore, sorry, no, we are setting that of L1 equals to 0. That's a ridge regression. Sorry. So when L1 is 0, this component will be removed. L1 is 0, we have alpha. So we have to set just the value of alpha in the ridge parameter. Yeah, here we have to set alpha. Alpha equals, let's say 0. or any value. L1 is 0. Here we set L1 0. No, okay. So here instead of 0.1, let's say this 0. Now I need to just show the impact of L1 equals 0. So here due to L1 0, it's not possible to fit the model of interest, but this is equivalent with that of a ridge regression. So here we have to directly fit a ridge regression model. So setting L1 equals 0 raises an error. Setting L1 equals 0 in the ElasticNet model raises an error. It doesn't automatically fit a ridge regression model. Therefore, we have to directly fit that of this ridge regression. Similarly, when you set alpha equals 0, these two components will be removed, or the penalties of both the L1 and the L2 norm will be removed. So we would expect the model to act like an OLS regression model. So again, if we try that, let's set alpha is equals to 0. This one, L1 ratio can be any value, let's say 0.5, and let me try. It raises an error because here alpha is 0, but when alpha is 0, we would expect the model to act like a linear regression model. So instead of fitting it using that of this ElasticNet, it is better to consider linear regression, which is an OLS regression and do not have a shrinkage effect in the linear regression. And then we have to fit the model of interest, and then one. So we have to just directly fit the OLS regression model. So when we use ElasticNet, setting alpha is equals to 0 or setting the L1 ratio to 0 results certain warning error. It actually just produces some results, but the results are not reliable. So it is better to fit the required model instead of utilizing the results that are obtained from the ElasticNet by setting is equals to alpha is equals to 0 and by setting that of L1 is equals to 0. So it's better to directly model the model of interest. So now let's see how to tune the ElasticNet's hyperparameters. Now in the ElasticNet's modeling, we have two hyperparameters, one alpha and the other this L1 or L1 ratio. So let's use as usual the grid search CV or grid search cross validation to tune these hyperparameters. So as usual, we have to instantiate our model of interest or the estimator. Let's say init ElasticNet. This is just an instantiation. Instantiation of our model of interest, not fitted. So the parameters by default alpha is 1.0, L1 ratio is 0.5. But now we are not going to utilize these values, rather we are going to search from a set of candidates values of these two hyperparameters. So here the first hyperparameter is alpha, let it be NP log space from -2 to 5. Just selecting 5 values from 10 to the power of -2 to 10 to the power of 2. So NP log space is nothing but this one, 0.01, 0.1, 1, 10, 100. and for that of L1 ratio, we use linear space from 0.001 to 1, and again let's select 5 evenly distributed values, linear space. So these values are 0.001, 0.25, 0.50, 0.75, 1. Now here I have two hyperparameters. Therefore, what the grid search does is that it is going to model a single model for each possible combination. 0.01 with 0.001, one model. For 0.01 to 0.25, another model. This one to this one, another model. Totally, here we have 5 values, and here we have 5 values. There will be 25 models. Of those 25 models, we are going to select the one that produces a better performance or better R-square. So here we define these hyperparameters here. The alpha values here 5, the L1 ratio values here 5. And totally there will be 5 times 5, 25 possible models to be fitted. I don't need here. Now we need to instantiate our model of that of the grid search. Our estimator or model of interest is init. This init is nothing but this one. And the other, we need to have also the parameter grids. The parameter grids are defined here, hyperparameters. So param grid equals parameters. And let's call this in grid. Then now this grid search CV is not fitted. We can look at the parameters. The estimator is ElasticNet. The parameter grid consists of alpha and also L1 ratio. These values are the ones that we have specified here, and these values are the ones that are specified here. So let me close this. So yeah, these are the default values, but these default values will be overridden by the hyperparameter values that are already specified in the param grids. Now we can fit this ngrid model. Just we need to call the fit method and supply the training data. Let me run. Now the model is fitted. Best value, let's say. Now the best estimator or the best hyperparameter values for alpha, it is 0.01, and for the L1 ratio, it is 0.75, right? These are selected of those values that are already specified from here. So we can also display the cross validation results. This is actually a dictionary that can be extracted from the grid models dictionary, but for ease of observation it is better to convert this into pandas data frame. So we can run. So here it says mean fit time, standard deviation, parameters, each possible combination. Totally we expect to have 25 models, so 24. Here the index starts from 0. That means these are the results for all the 25 models. So if we go to the last column, for example, it shows here 1. This is the best rank, 1. That means the model having a better performance. So the mean test score is this one, 69.1. Okay, so and the best hyperparameter values are alpha 0.01 and L1 ratio 0. Let me a little bit push. Yeah, alpha 0.01 and L1 ratio 0.75 with a mean test score of average test score of 69.1%. Specifically, just we can directly extract the optimal hyperparameter values of the two hyperparameters. So the optimal alpha is 0.01, the optimal L1 ratio is 0.75. Similarly, we can obtain its corresponding R-square value, that's the one that we saw already, that's here, rank 1, this one, 69.1. So we can use these attributes, best score, 69.1 to 5, this is the best score. Therefore, if we consider this as optimal hyperparameter values, we can fit our final model utilizing alpha this one and L1 ratio this one, or we can directly get, for example, the base training R square. We can call ingrid this one, the ingrid model this one, or the one this is trained. So ingrid score supplies the training data to obtain the train score. So if I run this, it becomes 0.73, but here we say it is 0.69. Now note that here it is the average of the 10 folds performance, but it is actually the train R square of the model utilizing only these optimal hyperparameters. But this R square is just the average of the 10 different folds. But this R square is just because we are supplying this training, and this training data is just provides the actual training R square utilizing for this train data set, but this is just the average of the 10 folds. Similarly, for the test, we can obtain the test R square 70. So we used just the ingrid or the grid search model, the grid search model here, this one and this one, or this one, the grid search model to obtain this train and test R square. Or otherwise, we can directly define any model with this optimal hyperparameter values 0.01, because it is 0.01. The optimal L1 ratio is 0.75, and then we have to fit the data. Now fitting is completed. Now we can call the score method and supply the training data to obtain the train score, and we have to call score and supply the test data to obtain the test score. So by fitting this new model using that of this optimal hyperparameter values, we obtain the train score 73.73, and the grid search model also obtains 0.7373, the same. Similarly, by defining a new model with this optimal hyperparameter values, we obtained the test R square as 0.7079. Similarly, using that of the grid models, it provides 0.7079. So this is the way that we tune hyperparameters when you have especially two or more hyperparameters. Just we need to define each hyperparameter in this form, and the grid search CV considers a model for each combination of the hyperparameters. Therefore, this is the way how we can train these penalized regression models and how to tune the optimal hyperparameters. So this is all about today's video. Next time we'll continue the machine learning models for specifically classification problems. Thank you for watching.